Welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video, we continue talking about priority queues, and we are going to implement our priority queue interface using a sorted linked list. Now, we could do this with a singly linked list, but for the reasons that we've seen when we wrote the linked list in the previous chapter, it's actually going to be advantageous to have a doubly linked list. It's going to simplify things. And while our normal queue and our normal stack, they were able to work very nicely with a singly linked list because, once again, they had a very limited form of things being added and things being removed. The methods for the priority queue aren't any more complex. However, the in-queue method for here is going to add things in a random location, or somewhat random. It's going to go into whatever location things should be in based upon the priority. Okay, so we want to have it, so this means that it could be added at the end, it could be added at the beginning, or it could be added anywhere in between. And that's exactly the type of scenario that led to special case coding if we used a singly linked list. So we're going to use a doubly linked list instead. So we'll go ahead and create a class. How about we do a sorted DLL priority queue. And we're going to make it so it can hold A's and it extends my priority queue. Okay, let's come over to the my priority queue and let's copy out these methods. We're making this based upon a doubly linked list, and as before, though I might be able to base this upon the mutable DLL, I actually want to spend time writing a doubly linked list because it is a significant skill for you to develop and for you to see over and over and over again. So we're going to have our node. Our node has the data. Actually, I believe the data can be a val here. We'll leave it as a val. However, I also feel very confident that the previous, which is a node, is going to have to be a var, and we're also going to have to make next a var. Just like with our mutable doubly linked list, I am going to create a sentinel. I'm going to call it end, and it will be equal to a new node. And for the purposes of this video, I am going to take the kind of sloppy but easier way of doing this, where I make an array of A of size 1 and pull off the 0th element and pass nulls in. And to make this work, private val. I'm waiting for my error to pop up over here. A has to have a manifest. The book does go over an alternative approach to this, but for this we're just going to go with having the end and using a default value in there. So ends next equals end, and ends prev equals end. Okay. So that sets us up with a doubly linked list. I'm not actually going to store how many things are in here, so the isEmpty is simply a check for end.next equal end, which is one of the conditions that we started with, and it's something we should get back to if we remove everything. Peak. Well, I want these to be sorted in an order such that the highest priority item is the head. So this will be as simple as end.next.data. DQ is also going to be rather simple. I want to remember the value at ends next data. So, and then I'm going to return that. And then I need to link around that. So the first thing I do is say end.next equals end.next.next. Okay. So skip over that one, and then link back. which is to say that end dot next dot prev. So since we just set end dot next to be the thing that is now following it, not the thing that was following it, we make it so that its previous pointer points back to end. Okay, 3 methods down, 1 to go. This is going to be the hardest one because this is, after all, supposed to be a sorted doubly linked list. And at this point we will find that we seem to be missing something. So I need to insert this new element into the correct location in the list based upon its priority. Okay. And the way I want to do this so that it goes, I also want to, for this implementation, preserve the kind of standard queue feature that if things have a tie in priority, the one that's been there longest will be pulled off first. So I want to walk from the end of the list and go backwards until I find an item that has the same or lesser priority. So rover equals end dot prev. Okay. And I'm going to keep going while, well, one of two possibilities. One, rover, I want to keep going while rover is not equal to end. If I get back around to end, I've gone back to the beginning, and it means that the thing that I've inserted has a lower priority than anything else on the list, so I should stop. So while rover is not equal to end, and while rover.data, now what I really want to be able to say here is that rover.data is higher priority, greater than O, but that's a problem because we don't have this operation. In fact, that's what it's going to tell us. Type parameter A doesn't have that. So if you think back a few chapters when we were talking about polymorphism, we ran into the same type of problem when we wanted to do a sort. We wanted to do a polymorphic sort, and we wanted it so it could sort anything. And we talked about a few ways of dealing with that, and one was to put constraints on A. But the other one, and the one that I personally prefer, is to provide a comparator, to provide a function that does a comparison between these things. And so I would like to pass in a function, we'll call it LT, for less than. In other words, it's going to return true if the first item has a lower priority than the second item. And it takes 2 A's for the comparison and returns a Boolean. So I want to keep going as long as the LT of O, comma rover.data is true. So as long as O is actually less than, or wait, do I want this? Let's go the opposite way. I want to keep going as long as, because I'm going to put high priorities in the front. So if the rover's data has a lower priority than O, then I need to move forward. And indeed, I've made this, I don't need brackets there, rover equals rover.prev. We're going to walk forward through the list because we started at the tail, and we're going to keep walking forward as long as the thing that we're on is less than what we're adding. If it's equal to or if it's greater than, as far as the priority goes, then we stop. Okay. We also stop if rover gets to end. So in other words, one way or the other, rover is going to be pointing at the node that should be before the thing we're adding. Okay. So now I want to add a new node and stick it after rover. To help make the logic easier to follow, I'm going to give this new node a name, N. This new node stores the value O. Its previous pointer is supposed to be rover, and its next pointer should be rover.next. Okay? Because as I said, rover is on the node that is prior to the thing that we are adding. Now we need to link these other two in. So I'm going to take rover's next prev first, rover.next.prev should link back to in, and then rover.next should link to in. Okay, so there's an implementation. We haven't tested it though. And so we're going to come back in the next video and we're actually going to run tests and see if this works the way that we want it to.